Hello everyone, my name is Justin Edgel, and I'm currently a student at Louisiana Tech University. My advisors for the project were Dr. Praveen Kumar and Kung Xuan Wang at the University of Illinois. My co-advisors are Bruce Rhodes, Allison Anders, Allison Goodwell, and Sarah Fisher. And I'm part of a group called CINet, the Critical Interface Network for Intensively Managed Landscapes. So my project is called Spatial Variations in Landscape Characteristics and Temporal Variations in Vegetation Cover. The objectives of my project were to look at these two things, landscape characteristics and vegetation cover over time. With the landscape characteristics, or with the elevation differences, it was the elevation in soil. And my objective was to see if the vegetation cover in these different elevations change over time. These are spatial and temporal characteristics that can have an effect on many environmental processes, and these environmental processes have an effect on the concentration of rivers and streams. So being able to understand the processes that affect the composition of rivers is critical for managing that river within a watershed. So I was in person for most of the internship, but all of my work was done on computers through programs, remote sensing programs that make it possible to study these things in a high detail. So my study area was in central Illinois, located along the upper Sangamon River Basin. My specific study area was Goose Creek subcatchment, which is basically just a mini watershed. I picked a smaller area within the upper Sangamon to get more accurate data. So the altered environmental processes that can be affected by the landscape characteristics and the vegetation cover are hydrological, ecological, and geochemical processes. Those hydrological processes are drainage, runoff, and evaporation. The drainage is what drains into the ground, and then that water underground drains into rivers and streams, and then the runoff is what happens on the surface of the land that drains into rivers and streams. And it brings the solutes into the rivers and streams that can affect the composition of these rivers and streams. And the ecological process is what happens with the vegetation and the trees. It's the water that is lost from these trees and plants, and that then goes into the atmosphere. The geochemical is the changing in the river composition. So evapotranspiration is the sum of evaporation and transpiration, the water that evaporates from the ocean and surface into the atmosphere, and then the transpiration is what leaves the plants, the water lost from the plants. So for the first part of my study was to look at vegetation cover over time, and this was done using a program called Planet Lab. The first image there is just what Planet Lab looks like, and what Planet Lab allowed us to do was to download images, daily images at a high resolution. The resolution being 3 meters, and in order to get this high resolution, we used their PlanetScope 4-band satellite. The 4 bands were important because we needed 2 of those bands to actually conduct a study on the vegetation. So we integrated Planet Lab into another program called Arcgis Pro, so we could actually study the vegetation using some of its features. So the first image here is going to be what Planet Lab looks like integrated into ArcGIS Pro. It allows us to search for images on wherever we want. Those little squares are going to be each section of the images. So the study was conducted from June 1st to July 25th. Basically, I searched for days with minimal cloud cover because you can't really study the vegetation if it's covered by clouds. So it was filtered for little to no cloud cover. And I was able to download 16 days between that time period. And then once I downloaded those images, I downloaded them as layers so I could conduct the study on all 16 of those images. And the study was conducted by calculating what's called a normalized difference vegetation index, or NDVI for short. And what that does is it gives us a value between -1 to 1 that displays the vegetation health and density of each single pixel in the image. So each 3-meter pixel gets a value between -1 and 1 And for the sake of scale, I used 0 and 1, 0 or the brown color being urban areas, buildings, and the dark green, the 1, are the healthiest types of vegetation. So the way an NDVI gets this value is that healthy vegetation absorbs red light and reflects near-infrared light, and unhealthy vegetation does the exact opposite. So that equation measures the difference of this to give a number between -1 and 1. And this was calculated on 16 days. What I did was clip each image. Since they were giant squares, I just clipped them to the specific Goose Creek subcatchment where I was conducting this study on. So the days that had minimal cloud cover were June 12th through June 21st. There were 16 days, including those days between there, where I was able to study the vegetation cover for this summer. So in order to study the landscape characteristics was a bit easier of a process. It's basically just downloading elevation data from the United States Geological Survey using LiDAR digital elevation models. LiDAR is a sensing technology that uses a laser to detect the ground, how long it takes to reach the ground, and then we get a number for the elevation. The scale here, 156 meters through 294 meters above sea level. And then once we get that data, I clip that to the Goose Creek subcatchment where I was conducting this study. So once I have that layer, I overlay that with the NDVI, the vegetation values, in order to conduct the study. So what I did was I created 6 small squares over the vegetation of the elevation data, and I gathered 39 points on those 6 squares. You can see on the bottom image, I calculated the points with respect to the elevation so I could see how dense or healthy the vegetation was with respect to the elevation. So the black points I gathered were the high elevation points collected on the red areas, and then right near it on the lower elevated areas, the blue and green areas, I collected the gray dots, which are the low elevation points. And I did that and collected 39 points total. And in order to get that data, I used what's called a workflow in another program called Model Builder. And as you can see, this is one of the study areas with a planet image that doesn't have vegetation values yet. It's just the image. So what I did, these are the attribute tables for each low and high elevation point. You can see they're empty right now because there's no values yet. So I run them through the process. First, I input the bounds where I did the study, the Goose Creek subcatchment, and then I input the red band for the planet image and the near infrared band for the planet image to calculate that vegetation index. And then I put in the low and high points so the values that it gets can be put into those points. So I run it, and the first thing it does is it clips the image to the Goose Creek study area, and then it takes that output and runs it through an NDVI calculator and gives us that value between -1 to 1. Then once it gets that value, it puts it into the low and high elevation points and puts it into the attribute table. So you can see now we have an NDVI value, 0.62 for the high elevation point, and for the low point, 0.76. And this was the process that I used in order to get my data. So for the results, what I found was that you can see in the graph on the bottom, the blue line is going to be the low elevation points. It's the average of all 18 of those low elevation points, or 19, excuse me. And then the red line is going to be the average of all those high elevation points. And of significance, what we found was that on the low elevation, the NDVI values were higher than compared to the high elevation for those specific study areas. And in the month of July, they evened out or were of not significant difference. So we were able to show that in these specific areas, the vegetation health and density is higher on lower elevations. And this is going to be a visualization of what one of those days in June looked like whenever the vegetation was higher in the lower elevated areas. This is another program called ArcScene, where it can project the layers as a 3-dimensional layers. And the first one's going to be the vegetation values, and then the second's going to be the elevation. So once I combine those, you can see that in the lower elevated areas, there's more dense vegetation, it's more green, and the data is exaggerated. There aren't actually mountains in that area. It's just to show the data, and you can see there's a lot of hills with yellow and brown areas to visualize that those areas with less vegetation in comparison to the lower elevated areas. So this study allowed us to, it gave us the information that for that part of the upper Sangamon River Basin, the vegetation cover was higher in lower elevations in those study areas for the month of June and then in July, the vegetation was able to catch up and were more or less equal. Why it was important to get this data was because this higher vegetation cover in these lower elevated areas can alter many environmental processes. And these environmental processes have an effect on the composition of the upper Sangamon River. They influence the solutes that go into there. So this data contributes to the climate change's effects on rivers and gives us valuable insight on how these space-time variations in a watershed impact our stream responses. Future research is going to be conducted on a flux tower and a river lab. The flux tower is what measures those environmental processes that are affected by the vegetation cover. And the river lab is what studies the composition of the river. The first picture on the bottom is what takes the samples from the upper Sangamon River, and then the second picture is the actual river lab that is able to measure the composition and the solutes within those samples of water in the river. And once they get this data later in the year or next year, something they could look back to see what might have affected or altered the composition of the river might be a study like mine where the vegetation cover was higher in these lower elevated areas. And then lastly, I'd like to thank Dr. Praveen Kumar and Kungjuan Wang for their constant help and support, and also access to the programs themselves that I used for the study, and then the National Great Rivers Research and Education Center for the organization of the project. And thank you. Any questions?
Yeah, so I have two. The first is, do you have much GIS experience when you started this?
Yeah, I've taken 3 classes using
Yeah.
ArcGIS.
Yeah, it was really nice.
Thank you.
Work. Yeah. And then, so as you were doing the project, what other data, GIS or remote sensing, were you thinking like, man, I could really use these data and that could give me more insights on this, or do you think you had everything you needed?
There were a lot of things I learned along the way, like using that workflow was something I was pretty unfamiliar with, so it's a learning process. A lot of research and my advisors helped to do those things. I guess I did know how to calculate the vegetation index. Didn't really know much about elevation data, so that was cool to see how that all worked.
Yeah. That's really nice.
Thank you. Yes.
Yeah, great work. I always wanted to look into some of this stuff for some of my wildlife research, and I was wondering, the NDVI, how does that, in terms of the signatures, like forest versus grassland or ag, is there like a signature there with just the NDVI layer itself?
So you mean the differences in what's on the ground, like what kind of vegetation?
Yeah, can you
Okay.
kind of?
Yeah, so that was why whenever I guess I picked the points near each other, because different areas, depending on what's there, like whether it's grass, trees, or just agriculture, the NDVI value will be different, because it does basically just use those 2 bands, the near infrared and red, and that basically detects the health of the vegetation. I think it's more of a greenness measurement. So I do believe that, I guess, maybe it depends on what it looks like on the image, the pixels, the colors. I'm not entirely sure if I am explaining that entirely properly, but to the best of my knowledge, that's how I'd explain it. Yes.
In the past, when I'd done NDVI, I used Google Earth Engine because I was always told that GIS was ran really slow. And I was just curious, like, how long do these models take to run in GIS?
So on my laptop, a long time. The data was like some of the data was like 40 to 50 gigabytes to, like, the elevation data was at least 40 gigabytes. So I had to use the University of Illinois computer with, very powerful. But yeah, it is a lot of data processing. So I couldn't do it on my laptop because it was so slow and like, but yeah, it's like a lot of gigabytes of data to manage. So, but yeah.
We have 2 questions from online. One is from Dr. Lisa Welp, and she says, great proof of concept, Justin. What do you think about the potential for automating this analysis to expand beyond 36 data points?
So we were actually working on a MATLAB algorithm that would automatically detect something else that's called topographic depressions in the different elevations, which basically would give us tons of more points, tons of more ways to find the data in an automation. Although I'm not very experienced with coding, I do imagine there are many algorithms that could detect those color signatures of high and low elevations and then just give us tons of data points based on that. Because it was 38 data points that I got. Definitely wasn't very much or as in-depth as it could have been. But yeah.
One more online question from Dr. Andrew Woke. Based on your ArcScene model, it looks as though there are some artifacts of image selection. There seem to be distinct large areas that are different from their neighbors. Do you have any idea of why this might be?
I do think there were a couple of areas that were actually buildings, which would have been the darkest yellow areas. And then there was actually a road and a river in there, and that seemed to kind of mess with what the layer was picking up. But yeah, it is exaggerated. If you do actually go to these areas in real life, you won't even notice you will hardly notice the elevation difference. With the program, I was able to expand so you can actually really visualize the differences in elevation. But those areas were probably a couple buildings, maybe some glitches with it picking up the road or a river. Yeah.
Any more questions for Justin? Thank you very much.